Hi everyone. In this lecture, we will see the complete summary of POSET. That means partial order relation. Okay, so let's start. First, we will see the summary, the definition of reflexive relation. What is a reflexive relation? If you have a relation R on set A, what is the definition of reflexive? So R is reflexive. R is reflexive if and only if and only if for every element of this base set, remember this A, this is our base set. On this set we are defining the relation. Okay, so this relation, you can see this relation is basically from set A to set A. Elements of A are related to elements of A. Okay, so here I can say that this relation will be reflexive if and only if every element of this base set is related to itself. Means for every element of this set A, I can say that A is related to A. Okay, so very simple definition that every element must be related to itself. This is the definition of reflexive relation that we already know. So you can easily see that every element is related to itself. Okay, then in this situation, this relation will be called reflexive relation. So I can say for all the elements in the base set, they must be related to themselves. This is the definition of reflexive relation, and this is how the graph will look like. The graph of reflexive relation, what will happen in the graph? You can see every element will have self loop because every element is related to itself. So in the graph of reflexive relation, every element is going to have a self loop. Okay, because reflexive means every element is related to itself. So you can see this pink element is related to itself, yellow element is related to itself, green element is related to itself, and this element also is related to itself. Okay, now let's see the transitive relation. What is the definition of transitive relation? So again, if you have a relation R on set A, on set A, so this set A, this is your base set. On this set we are defining the relation. So this is our base set. On the elements of this base set A, we are defining this relation. So I can say this relation is basically from set A to set A. Elements of A are related to elements of A. Okay, now when can I say that this relation which is on set A, when can I say this relation R is transitive? What is the definition of transitive relation? Okay, so this relation will be transitive if and only if, what is the condition? The condition is for all elements A, B, C, what must happen? For all elements of this base set, this A is our base set. So for all the elements, what must happen? This must happen that if if A is related to B and B is related to C, then A must be related to C. Okay, so very simple point. This is the definition that if A is related to B, B is related to C, then in the transitive relation, what should happen? That A must be related to C. Okay, so very simple point. So here remember, this will be called transitive A's. Okay, look at this A's. This is called transitive A's. We are going to call it transitive A's. Okay, so this is the definition of transitive relation. A relation is transitive if and only if for all the elements of this base set, I can say if A is related to B, B is related to C, then A must be related to C. Okay, so very simple. This is the definition of transitive relation. So you can see it here that whenever A related to B and B related to C, then A must be related to C. This is the definition. So for all elements, this should happen. Okay, very simple. Now what will be the graph look like? Okay, in the graph of transitive relation, you can easily see this pink is related to yellow, yellow is related to blue. Now you can see that transitively, you can see this is a transitive age, you can see pink is related to blue. Okay, so very simple. Look at this graph. This is transitive relation. You can see this element pink is related to yellow, yellow is related to green, and you can see this is transitive age, this pink is related to green. Okay, so you can see this is the graph of transitive relation. So if A is related to B and B is related to C, then definitely A must be related to C. Okay, so let me tell you about this graph of transitive relation. What you should take care in the graph of transitive relation. So two type of things you have to check. Okay, so one is this, that whenever you have this type of situation, let's assume A, element B, let's assume that you have bidirectional edges between them. What it means? It means that A related to B, B related to A. Now in this situation, for a transitive relation, what must happen? Tell me. what must happen? If your relation is transitive relation, then in this graph, what must happen? Between this a comma b, you have bidirectional edges, then definitely you must have self loop also. Okay, definitely. Why? What is the reason? Because you can see if a is related to b, B is related to A. Okay, you can see A related to B, B related to A. Then in this situation, transitively you can see, because this relation is transitive relation, so A will be related to A. Similarly, B is related to A is related to B, B related to A related to B. Then this transitive relation says that B must be related to B. Okay, so this is the first thing. This is the first thing. Remember that in the graph of transitive relation, if you have bidirectional edge between two nodes, then those two nodes must have self loop. Okay, if you have this bidirectional edge between two nodes, then those two nodes must have self loop. Okay, and this is the reason. Okay, now let's see what is another situation. Another situation is this, that if A is related to B and B is related to C, then remember, in the transitive relation, what must happen? A must be related to C. Okay, so these two things you have to check whenever a graph is given to you, and for that graph you have to check whether this relation is a transitive relation or not. Okay, now let's see the definition of antisymmetric relation. What is this antisymmetric relation? And this is quite interesting relation. Remember, again, if you have a relation R on set A, on set A, okay, then when can I say that this relation R is antisymmetric? I can say this R is antisymmetric. What is the definition? There are multiple ways to define this antisymmetric relation. Remember, this relation, we will say this relation is antisymmetric. So let's see the definition. If and only if, antisymmetric means that if two elements are different, for all a comma b, what you can say, for all a comma b, basically you can say that, okay, if they are different, if a comma b are different, okay, then at most one of these two things must happen. At most one of two things I'm giving you, at most one of either A related to B or B related to A, at most one of them must happen. At most one of them must happen. Okay, at most I'm saying at most one of them must happen. Okay, it is possible that both do not happen. Okay, it is possible that A is not related to B and B is not related to A. That is possible, but remember, at most one of them must happen. Okay, so this is one way to define antisymmetric relation. Antisymmetric relation, we can say that if you have two different elements, then at most one of them must happen. A related to B, B related to A, at most one of them must happen. Okay, what is another way to define, another way to understand this definition is, if A comma B, they are different, then what cannot happen? Okay, see, if A comma B are different, then the following cannot happen. Okay, then basically these two things together cannot happen. A related to B, B related to A, these two things together cannot happen. Together cannot happen. Okay, is this clear? Cannot happen. So this is how you can define the antisymmetric relation. If you have a relation on set A, then for all the elements, remember, for all A comma B, I can say, if you have two different elements, I am talking about different elements. If you have two different elements, then these two things together cannot happen. Okay, A related to B, B related to A, these two things together, they cannot happen. Let me tell you another way to define this antisymmetric relation. There are many ways. Remember, you can understand this antisymmetric relation in many different ways. So R is antisymmetric if and only if, again I can say, for all A comma B in the base set, what should happen? See, this should happen. Okay, if A is not equal to B and A is related to B, then what should not happen? Then tell me. If A comma B are different and A is related to B, then what should not happen? Then I can say B should not be related to A. Yes or no? Okay, if A comma B are different and A is related to B, then definitely I can say that B should not be related to A. Okay, so this is another way to define antisymmetric relation. And most useful definition, let me tell you, most useful definition, that is this, that relation is antisymmetric if and only if for all A comma B in this set A, what should happen? See, If these two things are happening, that A is related to B and B is related to A, then tell me in the anti-symmetric relation for A comma B, if this happens, then can they be different? Can A comma B be different? Tell me. In the anti-symmetric relation for element A comma B, if this happens, A related to B and B related to A, then can it happen that A comma B are different? No. Then in this situation, A must be equal to B. Okay, yes or no? So this is very famous. I can say this is most useful definition of anti-symmetric relation. I hope you understood. Okay, so remember there are two definitions that you should understand for anti-symmetric relation. You can use any of them. Okay, what is the definition of anti-symmetric relation? Anti-symmetric relation are on set A. Okay, so remember most useful definition is this. Most useful definition is that anti-symmetric relation means for all A comma B in the base set. Okay, for all A comma B in the base set A, what should happen? This should happen that if they are related, means A related to B and B related to A, if this happens, okay, if this happens, then definitely A should be equal to B. Okay, yes or no? Because in the anti-symmetric relation between different elements, this cannot happen. Okay, this same thing I can also say like this. This same thing I can say that, okay, I can say like this, that if they are different for all A comma B, I am saying that if they are different, if A comma B are different, then this cannot happen. Okay, yes or no? Then in this situation, I can say that A related to B and B related to A, this together cannot happen. And B related to A, this together cannot happen. This together cannot happen. Okay, so very simple. I hope you understood. Is this clear to everyone? Very simple, right? Okay, this together cannot happen. Okay, is it possible that none of them happens? Is it possible for A comma B? Is it possible that none of them happens? Yes, that is possible. Okay, but remember, they together cannot happen. Okay, one of them can happen, none of them can happen, but together they cannot happen. Okay, so very simple point. I hope you understood. Okay, so remember this anti-symmetric relation. Let me create a chart. Let me create a chart if A comma B are different in the anti-symmetric relation R. Okay, understand like this. See, anti-symmetric relation R on set A. Okay, this chart I am creating. What is allowed, what is not allowed. Okay, so let's assume that A comma B are different elements. Let's assume A comma B are different elements. Okay, they are different elements, and of course they belong to A. Okay, A comma B belong to A. They are from the base set and they are different elements. Okay, so if they are different elements, then remember what is allowed, what is not allowed. What is allowed and what is not allowed. See, A related to B, B related to A. What is allowed? Is this allowed that both of them are happening? Is this allowed? Both of them happen. Is this allowed in the anti-symmetric relation? In the anti-symmetric relation, both of them happen. This is not allowed. Okay, the other things are allowed. For example, this happens, this do not happen. This is allowed. This is allowed. This does not happen, this happens, or both do not happen. Okay, all these things are allowed. All these things are allowed. Okay, but remember this is not allowed. I hope you understood the definition of anti-symmetric relation. Okay, is this clear? That if you have two different elements, A comma B are different elements, then remember at most one of them can happen. Both of them together, they cannot happen. Okay, so these are the allowed cases. Very simple. Now let's move on. So you can see this is the anti-symmetric definition, that for all x comma y, I can say if they are related to each other, if x related to y, y related to x, then they cannot be different. Okay, then they must be same. So you can see very simple. So this is the idea. Okay, if A is related to B and A comma B are different, then B cannot be related to A. Yes or no? Agree? Okay, all these definitions are you understanding in the antisymmetric relation? If A comma B are different, and if A is related to B, then B cannot be related to A. Very simple. Okay, if A is related to B and B is related to A, then A must be equal to B. Okay, and in the graph, what should happen? Tell me. Antisymmetric relation graph, what should happen? Can anyone tell me in the graph of antisymmetric relation what should happen? The graph of anti-symmetric relation. What should happen? Tell me. In the graph of anti-symmetric relation, I can say between any two different nodes, you must have at most one edge. Yes or no? Okay, so very simple point that between two different nodes, between two different nodes, we cannot have bidirectional edges. Okay, we cannot have bidirectional edge. Very simple that between two different nodes we cannot have bidirectional edge. Okay, so this is the simple point. If you have two different nodes, then between them you cannot have bidirectional edge. Remember, self loop is allowed. Yes or no? Yes or no? Self loop is allowed. Okay, self loop is allowed. One thing you remember, the anti-symmetric relation, it only cares about different elements. That if two elements are different, if you have different elements, then they cannot have bidirectional edge. Okay, so remember, self loop is allowed because self loop is between same element, that is not between different elements, that is between same element. So self loop is allowed. Anti-symmetric relation has problem with only bidirectional edges between different nodes. That is the only problem. Okay, so you can easily see that between these two nodes, okay, there is unidirectional edge, this is fine. There is unidirectional edge, this is fine. There is unidirectional edge, this is fine. Self loop is allowed, there is no problem. Self loop allowed. Okay, you can have at most one edge between any two nodes. Okay, between any two nodes you can have at most one edge. Okay, you cannot have bidirectional edge, you can have at most one edge. So that is your anti-symmetric relation that we have covered. Now let's see the definition of partial order relation. This is our main topic. So far we have seen basically the revision, the summary of reflexive relation, transitive relation, and antisymmetric relation. Why I told you this summary? Why I gave you this revision? Because now we will see the definition of partial order relation, and now that will be useful. So what is the definition of partial order relation? When can I say that a relation is partial order relation? So let's see the definition. A relation A relation is partial order relation if it is reflexive, antisymmetric, and transitive. Okay, so these three properties must be there. If your relation is reflexive also and antisymmetric also and transitive also, then in this situation your relation will be called partial order relation. Okay, so very simple point that remember, if you have these properties, okay, your base set is A, your base set that is A, and on this base set you are defining a relation R. You are defining a relation R on this set A. What that means? That means you have a relation from set A to set A. Elements of A are related to elements of A. So now you have this relation on set A. Now when can I say R is partial order relation? This relation R, this is a partial order relation. This is partial order relation. In short, we will call it POR. So what is POR? That is partial order relation. So when can I say this relation is partial order relation? If and only if R is, all these three properties must be there. R is reflexive and antisymmetric and transitive. Okay, all these three properties must be there. So remember, you have to just check these properties: reflexive, antisymmetric, and transitive. These properties you have to check. And let me tell you, if R is a partial order relation on A, in this situation what will happen? So remember, if this relation R, on set A is a partial order relation, then remember, then there is a notation. This notation we use that this is the base set and this is your partial order relation. then this pair will be called, this pair is called POSET. This pair will be called POSET. Okay, we will call it POSET, partial ordered set. Okay, we will call it POSET. POSET means partially ordered set. Partially ordered set. Okay, so very simple point that if your relation is partial order relation, then in this situation, remember this pair where you have base set comma partial order relation, that is called POSET. Okay, is this clear? So you can say, now remember very simple point that you have base set, this is your base set, and on this base set you are defining the partial order relation. Now this complete thing is called POSET. This complete thing we call POSET. We call it POSET. Okay, is this clear? Very simple. Okay, now there is another notation also. Some people they use this notation also, that either you can write like this. Okay, some people they also write like this, R bracket A. Okay, is this clear? Both are same, but this is most famous. This is most famous. Is this clear? Let me know. Okay, so remember very simple point. If your relation on set A, that is partial order relation, in this situation this pair base set comma partial order relation, this pair will be called POSET. And remember, this relation will be partial order relation if you have these three properties: reflexive, antisymmetric, transitive. So very simple point that this pair A comma R, you can see here, this is called POSET. POSET means partially ordered set. Okay. Now let's see some standard partial order relations. This is what we need to see. One more thing I want to tell you, that these three properties, these are called RAT properties. This you can say R, antisymmetric means A, and transitive means T. So actually these three properties, in short, we call them RAT. Okay, RAT properties. So remember, in short, we are going to call it RAT properties. Okay, reflexive, antisymmetric, transitive. So a relation is partial order relation if these three properties are satisfied by the relation. Now we are going to see some standard partial order relations. So let's start one by one. First, these relations less than equal to, greater than equal to. These relations are partial order relation. Can you prove it? Can you prove that this greater than or equal to, this relation is a partial order relation on set of integers? Can you prove it? Please tell me. What you need to do if you want to prove it? On this set of integers, I am defining this relation greater than equal to. I am defining this relation. Now tell me, is this a POSET? Is this a POSET? So tell me, what you will prove if you want to prove that this is a POSET? What you need to do? Very simple. Remember, your base set is set of integers. Please understand. Your base set is set of integers. And what is your relation? Relation that you are defining. Your relation is greater than equal to. What that means? What that means? That means A is related to B if and only if A is greater than equal to B. Okay, is this clear? So this is the relation we are defining. A related to B if and only if A is greater than equal to B. And your base set, that is integers. Okay, that is integers that you already know. Okay, so tell me now what we need to do. Very simple. Is this relation reflexive? So first you check, is this reflexive relation? Tell me, this greater than equal to, is this reflexive relation on set of integers? Yes, this is a reflexive relation, because for every integer, what you can say, for every integer I can say that x is greater than equal to x. So definitely reflexive property is there. Yes or no? Okay, so I can say, because this happens, so I can say reflexive property is there. Yes. What about the next property, antisymmetric? What can you say about the antisymmetric property? Tell me, antisymmetric property. So tell me one thing. If A is greater than equal to B and B is greater than equal to A, what can you say? What can you say about A comma B? On the set of integers, your base set is set of integers. Now you tell me, on the set of integers, if A is greater than equal to B and B is greater than equal to A, in this situation, what you can say? This number A is greater than equal to B, this number B is greater than equal to A. In this situation, definitely they must be same. And this is the definition of antisymmetric relation or not? This is the definition of antisymmetric. So again, antisymmetric also, yes. Okay, very simple. What about the transitive? What can you say about transitive? Tell me. Transitive is also correct because you can see that if A is greater than equal to B and B is greater than equal to A, greater than equal to C. Okay, remember this is our relation. Okay, remember this is our relation. Our relation is greater than equal to. Okay, is this clear? Our relation that is greater than equal to. So you can see that this relation is transitive because if A is greater than equal to B and B is greater than equal to say C, then can we say A is greater than equal to C? Yes, definitely. Yes or no? Okay. So very simple. So that is the reason this is transitive also. So very simple point that this is the conclusion that this relation that we have defined, this relation greater than equal to on set of integers is a partial order relation. And because this is partial order relation, so what we can say? We can say this set of integers comma greater than equal to this is a POSET. Okay, we can say this is a POSET. So very simple point. Okay, similarly you can prove that less than equal to, that is also partial order relation. Less than equal to, okay, this is also, this relation is also reflexive, symmetric, antisymmetric and transitive. Reflexive, antisymmetric, transitive. So remember, less than equal to, greater than equal to, these relations are standard partial order relations because they are, these relations they are reflexive, antisymmetric and transitive. Very simple point. Yes or no? Okay, this is a note. What is the note? You can see this less than equal to or this greater than equal to, these are partial order relations on any set of numbers. Can I say? Can I say these are partial order relations on any base set, on any set of numbers? You can take any set of numbers. You can take base set equal to natural numbers, real numbers, integers, finite set, infinite set. Basically, any set of numbers you take. Can I say this relation will be reflexive, antisymmetric, transitive? Tell me. Tell me. We have already proven for set of integers. For set of integers, we have already proven that this relation is antisymmetric, reflexive, and transitive. Now you tell me these two relations, less than or equal to, greater than or equal to, these are partial order relations, means these are reflexive, antisymmetric, transitive on any set of numbers. You can take any set of numbers. Yes or no? Agree? Okay. Okay. Because remember, whatever set of numbers you take, remember your base set, you can take any set of numbers. It can be any random set of numbers. Okay, any random set of numbers. And if you take this relation, if you take this relation less than equal to, now tell me it will be reflexive or not? Tell me quickly, it will be reflexive or not? Let me know. Yes, it will be reflexive. Okay, any random set of numbers you can take. You can take finite set, infinite set, natural numbers, real number, integer. Okay, you can take any set of numbers you can take. Okay, then tell me this less than equal to, will it be reflexive? Yes, it will be reflexive because you can see for all numbers, for all numbers, what I can say? I can say that x is less than equal to x. Okay, is this clear? Please tell me. Okay, so you can see it will be reflexive. And second, it will be antisymmetric. It will be antisymmetric. What that means? If x is less than equal to y and y is less than equal to x, then definitely x will be equal to y. Okay, and similarly, it will be transitive also. Okay, it is going to be transitive also. So very simple point. If x is less than equal to y and y is less than equal to z, then I can say x is less than equal to z. Okay, so very simple point. Any random set of numbers you take, remember these relations will always be partial order relations. Okay, is this not clear? That your base set can be any random set of numbers. These relations less than equal to, greater than equal to, these relations, these are always partial order relations. If your base set is any set of numbers, okay, your base set must have numbers. Okay, now let's move on. Now tell me the answer for this question. To define the following relation, if you want to define subset or superset relation on set S, what should be the elements of set S? If I want to define subset relation on set S, then what should be the elements of set S? Please tell me. What should be the elements of set S? Very simple. elements of set S must be set themselves. Yes or no? They also must be set. Okay, is this clear? See, very simple point, that if you want to define this relation, I want to define this relation, that is subset relation. I want to define this subset relation I want to define. Okay, now you tell me, can you define this relation on this set 1 comma 2? Can you define this relation on this set? Okay, or can you define this relation on this set 1 2 1 comma 3? Okay, tell me, on which set you can define this relation. I want to define this relation, this subset relation I want to define. Then can you define this relation on this set? On this set we cannot define the relation. On this set we can define the relation. Yes or no? Is this clear? Okay, so tell me the valid base set. Valid base set. See, very simple point. On this set, can I define the subset relation? For example, does it make sense that 1 is a subset of 1? Does it make sense? Tell me, does it make sense? This is nonsense. Yes or no? This thing is a nonsense. Okay. So, but remember here this makes sense, that this set containing 1, this is subset of 1. This makes sense. For example, I can say set containing 1, this is subset of 1 comma 3. Makes sense. Okay, very simple point. I hope you understood. So remember, if you want to define this subset relation, then your base set must contain set. Is this clear? Please tell me, is this understood? This is your base set, and in your base set, every element must be a set. Every element should be a set. Okay, please tell me, is this clear? Let me know. So very simple point. This is the point. Remember, if you want to define this subset or superset relation, then remember your base set elements must be set. In your base set, every element must be a set. Agree or not? Is this clear? Please tell me. Let me know. So very simple point. Now let's move on. Now let's see another standard partial order relation, that is subset comma superset. These are standard partial order relations. Okay, remember, in your base set, every element must be a set, where elements in the base set are set, because only in this situation, when your base set elements, every element is a set, in this situation these relations we can define, right? Yes or no? Okay, so very simple point, that these are also partial order relations, subset comma superset. Okay, is it necessary, if you want to define this subset relation, is it necessary that your base set must be a power set? If you want to define this subset relation, then is it necessary that your base set must be power set of some set? Is it necessary that base set is equal to power set of some set? This is not necessary. Okay, this is not necessary. But remember, very simple point, if you want to define this relation, then your base set elements must be set. Very simple point, to define, I want to define this subset comma superset relations. Okay, if I want to define these relations, then very simple point, these relations must be defined for set. Yes or no? So your base set must be like this. In your base set, everything must be a set. For example, this also must be a set. For example, this also must be a set. Yes or no? Is this clear? For example, this also must be a set, and so on. Okay, so every element in your base set must be a set. Very simple point. It is not necessary that your base set is a power set of some set. It is not necessary. Yeah, this is also fine. If your base set is power set of some set, then is that fine? Please tell me. If your base set is power set of some set, then is that fine? Yes, that is fine. Because in the power set, every element will be a set. Yes or no? In the power set, every element also will be a set. So that is fine. Okay. Now let's see. So these relations, subset comma superset, these relations, these are also partial order relation. Okay. So you can easily see that if your base set is like this, where every element is a set, remember, you can see here every element is a set. Correct. Now, can you prove that this is a partial order relation? How to prove? Tell me. Remember, here your base set is this is your base set. Now you tell me, this is our base set. On this set, we are defining the relation. Okay. And here you can easily see every element is a set. This element, this is a set. This element, this is a set. Okay. So every element is a set. Now, I want to know this subset relation. How will you prove that that is a subset relation is reflexive, antisymmetric, transitive? Yes. You can see reflexive. Why this is reflexive? Because every set is subset of itself. Yes or no? You already know that every set will be subset of itself. This we already know that every set is always subset of itself. So this always happens. Okay, for every set. Correct. Okay, so very simple. Every set is subset of itself. So reflexive property is satisfied. Okay, because every set is related to itself. What about the antisymmetric property? Antisymmetric property is also satisfied. If you remember your set theory, in set theory, what we have seen, do you remember? We have seen that if A is a subset of B and B is a subset of A, what you can say in this situation? This is the definition of set equality. In the set theory, we have seen if A is subset of B, B is subset of A, in this situation, A will be equal to B. And the third point, that is transitive. That is transitive. Yes, subset relation is transitive also. Okay, because if A is subset of B and B is subset of C, then I can say A is a subset of C. Yes or no? Is this clear? So very simple point. Okay, so these properties are there. That is the reason I can say subset relation is partial order relation, because it is reflexive, antisymmetric, transitive. Okay, so very simple point. Remember, if you have any collection of set, okay, is this point clear? If you have any collection of set, this is your base set, which is a collection of set. Okay, which is a collection of set. This is a set. Remember, this is a set. Okay, so in this situation, remember, this is subset relation. This subset relation on this P is a partial order relation. Okay, that will always be a partial order relation. Is this clear? Now, very simple point. So you can easily see that these relations, these relations are partial order relations. Okay, I hope these points are clear. So remember, tell me one thing. These relations, they are partial order relation, means reflexive, antisymmetric, transitive. If your base set is any set of sets, yes or no? Your base set can be power set, or your base set can be any random set of set. Okay, in that situation, these relations are going to be partial order relation. Is this clear? Please tell me. Okay, so your base set can be any set of sets. In this situation, these relations will always be partial order relation. Your base set can be power set, that is also fine. Your base set can be random set of sets, that is also fine. Okay, let's move on now. Now let's see this. Another standard partial order relation I want to tell you, that is divides relation, or I can say divisibility relation, or you can say divides relation on set of natural numbers. Okay, if your base set is set of natural numbers, then this divides relation, this is a partial order relation. Okay, so can you prove it? Tell me, can you prove it? You can see this is your set of natural numbers. Yes or no? This is your set of natural numbers, or I can say this is set of positive integers. Okay, so tell me, I am defining this relation. I am saying that A is related to B if and only if A divides B. Okay, this is the relation. What that means? This means A divides B. Okay, again you tell me quickly, is this reflexive? Will this be a reflexive relation? Yes, this will be a reflexive relation, because remember, your base set is this. This is your base set 1, 2, 3, and so on. This is set of natural numbers. So tell me, can I say every number, every positive integer, every natural number divides itself? I can say for all a belonging to the natural number, I can say a divides a. That is true. 1 divides 1, 2 divides 2, 3 divides 3. Yes or no? So this relation is definitely reflexive. What about antisymmetric relation? Yes, this is antisymmetric also. Okay, because you can easily see this is your base set. Your base set is 1, 2, 3, and so on. Set of natural number. Now you tell me, now you tell me, if A divides B and B also divides A, then what you can say about A comma B? This is your base set 1, 2, 3, and so on. Okay, so if A divides B, B divides A, then definitely I can say A is equal to B. So that is the definition of antisymmetric relation. What about transitive relation? Transitive relation. Yes, this is transitive also. You already know that. If A divides B and B divides C, then definitely A divides C. Okay, so this is the idea. Is this clear? Okay, understood. Very simple. So transitive property is also satisfied. So very simple that if you have base set is set of natural numbers, then remember this divides relation. This is a partial order relation. Okay, so this is another standard relation. Now this is a question that I want to ask. Tell me the answer for this question. Which is a partial order relation? This divides relation. This divides relation. Can I say on every base set it will be a partial order relation? Can I say this divides relation? Can I say it will be reflexive, antisymmetric, transitive on every base set? On every base set? The answer is no. The answer is no. Remember, on set of natural numbers, yes, this is a partial order relation. But on integers, on real numbers, this is not partial order relation. Can you tell me why? Can you tell me what is the reason? See, on set of integers, if I define this relation, divides relation, now this is a now this is not antisymmetric. Yes or no? Now this is not antisymmetric. Tell me why? Why this relation is not antisymmetric? Because you can see 1 divides minus 1, 1 is related to minus 1, and minus 1 is related to 1. Yes or no? Is this clear? Even if you take non-zero numbers, then also this will not be antisymmetric. For example, if I take non-zero integers, integers minus 0, now tell me, is this a partial order relation? If I take non-zero integers, still this is not antisymmetric. Still this is not antisymmetric. Why? Because you can see 2 divides minus 2 and minus 2 divides 2. Is this clear? Please tell me. Let me know. Understood? So you can see different elements, 2 comma minus 2, they are different elements. Okay, because of this situation, I can say this relation is not antisymmetric. So did you understand that for the divides relation, the base set matter or not? For this divides relation, the base set will matter or not? Yes, it will matter. Okay, tell me one thing. So far, we have seen three relations, we have seen three standard relations we have seen. The first was less than equal to, the second was subset, and the third is divides. In which of them the base set matters? Tell me. The base set, you should focus on the base set. For which of them? So you can see for the divides relation. Remember, less than equal to, that is always partial order relation. If your base set is set of numbers, any set of numbers you can take, this less than equal to, greater than equal to, they are partial order relation. Similarly, this subset and superset, they are always partial order relation as long as your base set is a collection of set. Okay, but this divides relation, this is a, for this divides relation you should take care what is the base set. Is this clear point? Please tell me, is this point clear? That so you can see this is correct and these are not correct. Okay, so finally this is the note that you should take care when the relation is divides. Is this clear? Let me know. When the relation is divides relation, then you should take care. Okay, because remember, this divides relation, this is a partial order relation on set of positive integers, on set of natural numbers, on set of positive integers. Yes, this is a partial order relation, but remember, but not on integers or real numbers. Okay, is this clear? So take care when the relation is divides relation, you should take care. Okay, now let's move on. Let's solve this question. Tell me the answer quickly. This question is taken from Kenneth Rosen book. Which of the following relations on 0, 1, 2, 3? This is the base set. Yes or no? Okay, your base set is 0, 1, 2, 3. So, which of these relations? Some relations are given to you. Which of these relations are partial order relations? So, for partial order relation, which properties you should check? Tell me. You should only check reflexive, antisymmetric, transitive. The first one, is this reflexive? The first one, this is not reflexive, right? Because reflexive says that every element should be related to itself. Why this is not reflexive? Because one is not related to one. Okay, one is not related to one. So this is not reflexive. Yes or no? Because it is not reflexive, so this is not partial order relation. Okay, what about the second one? 0 related to 0, 1 related to 1, 2 related to 2, 3 related to 3. So reflexive property is there. What about antisymmetric property? Do we have antisymmetric property? You can see between different elements. Are you getting A related to B, B related to A? Are you getting that? No, we are not getting that. So antisymmetric is also there. Okay, antisymmetric is also there. What about the transitive? For option B, remember to check transitive the best way. What is the best way? If you want to check transitive property, what is the best way? The best way is to create a graph. Okay, so just create a graph 0, 1, 2, 3. These are the nodes. Okay, there are self loop because this is reflexive. Option B is reflexive. Now you can see 2 related to 0, 2 related to 3. Okay, so you can see 2 related to 3, 2 related to 0. Is there any violation of transitive property? Do we have any violation of transitive property? There is no violation of transitive property. Okay, so definitely I can say this is a transitive. Okay, this is transitive. So very simple. This is your partial order relation. Okay, what about the next? Option C. Tell me about option C. In option C, 0 related to 0, 1 related to 1, 2 related to 2, 3 related to 3. So yes, this is reflexive. There is no problem there. What about antisymmetric? Between different elements, do we have A related to B, B related to A, this type of situation? We don't have that situation. So this is antisymmetric also. Okay. What about transitive property? For option C, again, for option C, let's check the transitive property. To, to check transitive property, what you will do, just create the graph representation. That is the best way so that you don't make any mistake. Okay, if you want to check transitive property, just create the graph. So you can see 1 related to 2, 3 related to 1. 1 is related to 2 and 3 is related to 1. Is there any violation of transitive property? Yes, there is violation. Okay, there is a violation of transitive property. What is that? The violation is like this. You can easily see 3 is related to 1, 1 is related to 2, but you can notice 3 is not related to 2. 3 is not related to 2. So that is the violation. So definitely I can say that this option C, that is not transitive. Okay, not transitive. What about option D? Tell me. Let's check option D. 0 related to 0, 1 related to 1, 2 related to 2, 3 related to 3. Okay, so reflexive property is there. There is no problem. Okay, you have reflexive property. What about the antisymmetric property? Is there any violation of antisymmetric property here? Between different elements, do you have A related to B, B related to A, this type of situation? So you can see 1 related to 2. Are we getting 2 related to 1? No. 1 related to 3. Is 3 related to 1? No. 2 related to 0. Is 0 related to 2? No. 2 related to 3. Is 3 related to 2? No. Okay. 3 related to 0. Is 0 related to 3? No. So you can see this is antisymmetric also. And what about the transitive property? This relation, is this transitive or not? Students are saying this is not transitive. What is the counter example? This is not transitive, and you can easily check that with the help of graph. Okay, so for option D, again you check for transitive property. Let's again create the graph 0, 1, 2, 3. Okay, you can see everyone has self loop because option D, that is reflexive. So everyone has self loop. Next, you can see one related to 2, one related to 3. Okay, one related to 2, one related to 3. Next, you can see 2 related to 0, 2 related to 3. So you can see 2 related to 0, 2 related to 3. Okay, and after that, 3 related to 0. Okay, after that, at the end, you can see 3 related to 0. Okay, so do we have violation of transitive property? Tell me, is there any violation? So you can easily see that 1 related to 3, 3 related to 0, but 1 is not related to 0. Yes or no? There is violation here. Okay, so let me tell you the violation. Violation of transitive property. You can easily see that 1 is related to 3, 3 is related to 0, but 1 is not related to 0. Okay, so this is how you can see that this relation, this is a not a transitive relation. Okay, is this clear? So very simple point. And option E I am giving you as a homework. Okay, so please comment. This is your homework. You can please pause the video, solve this question, and put your answer in the comments. So this is the homework. Okay, let's move on now. Now let's solve this question. This is another question from Kenneth Rosen. The question is saying which of them are POSET. So tell me, is this a POSET? Set of integers, comma, equal. Okay, see equality. This is reflexive. Yes, this is reflexive. Is this anti-symmetric? Yes, this is definitely anti-symmetric also. There is no violation of anti-symmetric. Yes or no? Between different elements, if A, comma, B are different elements, then can you have A related to B and B related to A? You cannot have. Yes or no? Very simple. So this is anti-symmetric also. And this is transitive also. So yes, this structure, this is a POSET. Okay, this first one, this is a POSET. Okay, is this clear? Yes, this is transitive also. If A equal to B, B equal to C, then definitely A equal to C. So this is transitive also. What can you say about option B? Z comma not equal to. This is not partial order relation because this is not even reflexive. Yes or no? This is not even reflexive. You can easily see that in this you can easily see that, for example, 2 is not related to 2. Yes or no? 2 is not related to. Okay, is this clear? Very simple, because your relation is not equal to. So remember, 2 is not related to 2. So this is not reflexive. What about anti-symmetric? What about anti-symmetric? This is not anti-symmetric. What is the reason? See, the reason is 1 related to 2 and 2 related to 1. Okay, so this is not anti-symmetric. What about transitive? This is not transitive also. This is not transitive. Why this is not transitive? Let me tell you. Because you can see 1 related to 2, 2 related to 1, but 1 is not related to 1. Okay, is this clear? Please tell me. So remember this option B, this is not reflexive, not anti-symmetric, not transitive. Okay, let's see the next option. What about this one? Z comma greater than equal to. I told you this greater than equal to, this is always partial order relation. I told you this. Do you remember? Okay, for any set of integer, for any set of numbers, you can take any set of numbers here. Okay, I can take any set of numbers. This greater than equal to, this is always partial order relation. So this, yes, this is a partial order relation. Okay, what about Z comma not divides? This means not divide. Okay, yes or no? Not divide. So here, this is not a partial order relation. Why? Look at option D. Option D is Z comma not divide. So you can easily see this is, first of all, this is not reflexive. Okay, because you can easily see that 2 is not related to 2. This is not anti-symmetric also. Why this is not anti-symmetric? Because 1 is related to 2 sorry, not divides, not divides. So you can see 2 is related to 3 and 3 is related to 2. Okay, so this is not antisymmetric because 2 related to 3. You can see 2 does not divide 3, 3 does not divide 2. So very simple that this is a not antisymmetric. Okay, and what about transitive? This is not transitive also. Okay, why this is not transitive? This relation is not transitive because you can see 2 is related to 3, 3 is related to 2, but 2 is not related to 2. Yes or no? But 2 is not related to 2. So very simple. Please tell me, is this point clear? Let me know. So in this question, what will be the answer? Which of the following are POSET? So this is a POSET, this is a POSET. The answer will be option A, comma C. Okay, let's move on now. Tell me the answer for this question. This question is also taken from Kenneth Rosen. Question number 6. Which of the following are POSET? R, comma, equal to real numbers. R means real numbers. Here remember R, that is set of real numbers. So what about equality? Yes, this will be a partial order relation because remember this equality, this is reflexive also. Okay, you know A equal to A. This is antisymmetric also. And this is transitive also. Okay, so very simple that this will be, this is definitely POSET. Less than, this is a not reflexive. Okay, yes or no? Actually, this is antisymmetric. This is actually antisymmetric. This is actually transitive also. But this is a not a reflexive. So I can say option B is gone. Okay, is this clear? What about less than equal to? I told you what about this? Tell me, what did I tell you? This is always a partial order relation. You can take any set of numbers. Okay, so this is always. What about this not equal to? So this is a not, you already know. This is not reflexive. You already know this is a not antisymmetric. And this is a not a transitive. Okay, so very simple. So for this question, the answer is what? That is also A, comma C. This is from Kenneth Rosen. Question number 9, 10, 11. So graph representations are given to you. Which of them is partial order relation? Quickly tell me. What about this question number 9? This is the graph representation A, B, C, D. So you can see every node has a self loop. So this is reflexive. Different nodes, do they have bidirectional edges? Between different nodes, do we have bidirectional edges? No. So that is the reason I can say this is antisymmetric also. Okay, what about transitive? Is there any violation of transitive property? Yes, there is violation of transitive property because A related to B, B related to D, but A is not related to D. So there is violation here, right? Okay, you can see we have a violation here. So transitive property is not satisfied. So definitely this is not a POSET. Okay. What about this question number 10? This graph is given to you. In this graph, you tell me. Again, reflexive property is satisfied because every node has self loop. What about antisymmetric property? Different nodes, do they have bidirectional edges? No. So that is the reason this is antisymmetric also. What about transitive property? What about the transitive property? Tell me. Is the transitive property satisfied? No, transitive property is not satisfied because C related to D, D related to B, but C is not related to B. Okay, so transitive property is not satisfied because C related to D, D related to B, but C is not related to B. So that is the reason transitive property is not satisfied. So this is also not a partial order relation. Okay, what about this next? Question number 11. In the question number 11, this is the complete graph. Okay, remember, this is your graph. So you can see here, every vertex has self loop. So this is reflexive. Antisymmetric property, yes, antisymmetric property is satisfied, there is no violation. And transitive property is also satisfied, there is no violation. Okay, so yes, this is a partial order relation. Okay, very simple. Now let's move on. Now let's see the abstract partial order relation notation. So far we have seen many different partial order relation. This is the abstract notation. This notation is the abstract notation for partial order relation. So remember, when this notation is given, it simply means that this is a partial order relation. So this is same as partial order relation R. Okay, is this clear? So remember, some people what they will do, they will give you like this set A comma R, or some people they will give you like this set A comma this symbol. Okay, is this clear? So very simple point, this is just a symbol, nothing else. This is just a symbol for partial order relation. For partial order relation. Okay, this is just an abstract symbol for partial order relation. For example, remember this structure we have seen. I'm writing some posets here. Some poset I'm writing here, and you tell me what is this symbol in all of them, in all these structure, because this is abstract symbol. Remember, this is abstract partial order relation symbol. Okay, but you can easily see that if I give you this structure, for example, set of integers comma less than equal to. Now here what will happen? Now this is partial order relation, so here you can see that this symbol is actually same as this. Is this clear? Okay, similarly if I give you this structure, set of natural numbers comma divides, here also you can easily see that this symbol here, this symbol means divides. Okay, agree? Similarly if I give you this power set of A comma subset, so here this symbol is same as subset. Okay, so very simple point, this is just a symbol for partial order relation. Okay, so don't confuse this with less than equal to. Is this clear? Do not confuse this symbol with the less than equal to symbol. This is just a partial order relation symbol, nothing else. Okay, you can easily call it R. Simple. In simple words, you can say that this is just partial order relation R. Okay, for example, you can see here, if this is your base set, in your base set every element is a set. Here you can easily see that I can say, basically you can see partial order relation is subset. Yes or no? Is this clear? Please tell me. So remember, this is just a symbol for partial order relation. This is just partial order relation symbol. But actually, what is the relation? Actually, this is the actual relation. Actual relation is this subset. Okay, so very simple point. You can easily see one more thing here. This is just a partial order relation symbol, right? This is just a partial order relation symbol. Okay, you can easily see. Actually, it means divides in this question. So in the first question, this symbol means divides. In the second question, this symbol means subset. Okay, let's move on. For example, look at this GATE Computer Science 1996 question. Okay, in this question, this set is given to you 2, 3, 6, 12, 24. Look at this. The question is saying, let this symbol be partial order defined by x is related to y if x divides y. So tell me here you tell me what is the actual operation. Read this line and tell me what is the actual relation. What is the actual partial order relation? Tell me what is the actual relation here. The actual relation is divides. Okay, is this clear? The actual relation is actually divides. I hope you understood. So remember, the question is saying that this symbol is partial order defined by x is related to y if x divides y. Okay, so here actually remember, in this statement you can see this, what this reads. How will you read this? Tell me, how will you read this? In this complete statement, this is the complete statement. In this complete statement, how will you read this? This is, okay, we read as x related to y. Okay, don't read x less than equal to y. Okay, is this clear? Don't read that x is less than equal to y. Don't read like that. Okay, so I hope you understood this. So this is your gate exam question. Just to confuse, some students will get confused, and that is the reason this, you can see, this is given to you. So the question is saying that this symbol is partial order defined by x is related to y if and only if x divides y. Okay, is this clear? So remember, your set was actually this. Your base set is 2, 3, 6, 12, and 24. This was your base set. And the question is saying that A is related to B if and only if A divides B. Okay. Again, I'm telling you, this just means related. A is related to B if and only if A divides B. So now you tell me, is this statement true? 2 related to 3. Is this statement true or false? Tell me about this. 2 related to 3. This statement is actually false. Okay, why? Because actually this means this is same as 2 divides 3, and that is false. Okay, yes or no? Okay, so remember, very simple. If you confuse, some students who don't know about this, they will get confused and they will think, yes, this is true. Yes or no? They will think that this is less than equal to. No, this is not less than equal to. The question is clearly telling you that this is just a symbol for partial order, nothing else. Okay, it is just a symbol for partial order relation, but actually the relation is x is related to y if x divides y. Okay, so very simple. So can I say that 3 is related to 6? Yes, this statement is true. Okay, this statement is true because actually this will mean that 3 is 3 divides 6, which is true. What about 6 is related to 3? This statement is false. Okay, because remember, here this actually means 6 divides 3, which is false. Okay, let's move on. Now let's see comparable elements in a POSET. When can I say two elements are comparable in a POSET? So let's see the definition of comparable element. If you have a POSET, if you have base set A, comma R, if this is your POSET, okay. If this is a POSET, then can I say R is partial order relation? Yes, R is partial order relation, and this A, this is your base set. Okay. So if this is a POSET, then when can I say two elements are comparable? What is the definition of comparable? So remember, A comma B, they belong to base set. Now A comma B are comparable. They are comparable. You can compare them. They are comparable if and only if either A is related to B or B is related to A. Either A is related to B or B is related to A. Is this clear? So this is the definition of comparable. A comma B are comparable. You can say that these two elements are comparable if either A is related to B or B is related to A. This is the definition of comparable elements. Okay, and what is the definition of incomparable elements? When can I say A comma B are incomparable? Not comparable? What do you think? What is the definition? Incomparable. Incomparable simply means that this will mean that A is not related to B and B is not related to A. Yes or no? A comma B, they are not related to each other. Because remember, if A related to B or B related to A, then in this situation, you will say these two elements are comparable. Okay. These two elements will be incomparable if A is not related to B and B is not related to A. So this is the definition of comparable and incomparable elements. You tell me about this structure. Z plus comma divides. We already know this is a POSET. We have already seen this set of positive integers comma divides relation. Now here you tell me, are they comparable? 3 comma 9 in this structure, in this POSET, are they comparable? The answer is yes. Why? Because you can see 3 is related to 9. Okay, because 3 is related to 9. What about 5 comma 7? Are they comparable? Are these two comparable? 5 comma 7? Tell me. They are not comparable. Why? Because you can see 5 is not related to 7. 5 does not divide 7 and 7 does not divide 5. Yes or no? Okay, so you can see that 5 is not related to 7 and 7 is not related to 5. Okay, I hope you understood this simple point. Okay. Now let's move on. What about this question? Tell me the answer quickly. Find incomparable elements in the POSET. What is this? Can anyone tell me? This base set. What is the base set? How many elements are there in the base set? How many elements are there in the base set? This is power set of 0, 1, 2. Okay, so actually in the base set, there are 8 elements in the base set. Okay, and your relation is subset. This is a partial order relation, you already know. Okay, now you tell me which elements are incomparable. Incomparable means, when can I say two elements are incomparable? Incomparable means x is not related to y and y is not related to x. X is not related to y and y is not related to x. This is the definition of incomparable. So you tell me here, can I say this is subset of 1 comma 2? No. Can I say this is subset of 1 3? No. So you can see, yes, they are incomparable, because you can notice this element is not subset of this element and this second element is not a subset of this element. So I can say they are incomparable. What about these two? Yes, they are also incomparable. These two, they are actually comparable. Okay, they are actually comparable. Why they are comparable? They are comparable because this element is a subset of this second element. So I can actually say that this first element is actually related to the second element. So they are actually comparable. What about this one? Yes, they are also comparable. These two elements, they are also comparable. Why they are comparable? Because you can see this element is a subset of 2 comma 3. Okay, so they are also comparable. Very simple. Okay, what about this last one, 1 comma 2, 1 comma 2 comma 3? Yes, they are also comparable. Okay, because this is subset of this. So for this question, the answer will be option 1 comma 2. Is this clear? Let me know. So very simple. Actually, the base set is 1, 2, 3. Okay. For this question, the base set is actually by mistake. This is a mistake. It is 1 comma 2 comma 3. There is a mistake here. This is not a tricky question. This is just a mistake. Okay. Tell me the answer for this question quickly. In the list below, select all pairs which are incomparable elements in the POSET power set of A, where A is A, B, C, D, E. So again, we have to find the incomparable elements. The relation is subset. The relation is a subset relation. This is the subset relation. So what about ABC, ADE? They are not subset of each other. So yes, they are incomparable. The question is asking incomparable. They are incomparable. They are not subset of each other. They are also incomparable. This is actually subset of this. Okay, so they are actually not incomparable. The question is asking incomparable. So you can see here this element is actually related to the second element. BCD, ABCD. Here also the first element is actually related to second element. So they are comparable. ABC, BC. This second element is related to first element. So they are actually comparable. And these are also not comparable. Okay. So for this question, the answer will be first option, second option, and last option. Let's move on. Now let's see total order relation definition. What is the definition of total order relation? The definition of total order relation is actually very simple. What is total order relation? Let's see. You need two things for total order relation. What are those? First, it must be a partial order relation. It must be a partial order relation, and every two elements must be comparable. Every pair of elements comparable. Every pair of elements must be comparable. This is the definition of total order relation. Is this clear? Very simple. Definition is very simple. It must be a partial order relation. So because of that, it is reflexive, antisymmetric, and transitive. Okay. So also, this is the condition that every pair of elements must be comparable. Then in this situation, you will call it total order relation. There are different names for it. Either you can call it total order, or you can call it linear order, or you can call it chain. Okay, linear order, or you can call it chain. So these are different names. Some people also call it simple order. Okay, there are some authors, they call it simple order also. So you can see total order relation, that is also called linear order, or you can call it chain, or you can call it simple order. These are different names, but you can see this is the condition that it must be a partial order relation and every pair of elements must be comparable. Okay, for example, this z comma less than equal to, tell me, can I say this is total order? Look at this z comma less than equal to. Can I say if I give you two elements, can I say definitely they are comparable? Let me know. If I give you two elements from integers, two integers I give you, can I say definitely they will be, one of them will be related to another? Yes, definitely. This is a total order relation. Okay, yes or no? This is total order relation. Because if I give you any two elements, for example, if I give you 5000 comma minus 300, now you tell me, are they comparable? Are they comparable? Yes, they are comparable. Why they are comparable? They are comparable because this minus 300, this is related to 5000. Okay. So very simple. This is total order. What about the next one? What about this next one? This positive integers comma divides relation. Now here can I say every pair is comparable? Every pair of elements is comparable. You can easily see 2 comma 3 are not comparable. Okay. So immediately what you can say? You can say this is a, yes, this is partial order relation, but not a total order. In the next session, we will see hash diagram of the POSET.